Last week, remember, we were sort of like learning our ABCs of organic chemistry structures here, right? Just how to look at structures, how to understand structures. This week, we're going to learn how to read, how to manipulate these structures using what are called electron pushing arrows. So, first thing we're going to do is just take a look at a simple reaction, one that you would have studied before quite a bit in 1B, an acid-base reaction. All right, let's say between hydroxide and hydrochloric acid. Does anybody remember what the product of these reactions would be? What's one of them? Water, right? So we got water in our acid-base reaction, and the other one would just be a chloride ion, okay? Great, so we're used to looking at these balanced chemical equations, but again, it's all about the structures here in organic chemistry. So everybody take a second and draw me the Lewis structure of these molecules here with their electrons. All right, so my hydroxide ion, if oxygen has this -1 formal charge, how many lone pairs should I be putting on there? 3. Right, and HCl, chlorine likes to have 1 bond and 3 lone pairs. When we get to H2O, now oxygen's happy, it's got its 2 bonds, so it just needs 2 lone pairs. And what about my chloride ion? How many lone pairs should chlorine have? 4, right? So when it's got that -1 formal charge, we need all 4 lone pairs. Okay? So, great. We're not going to be looking at our reactions as simply as these like one-line balanced chemical equations. We want to look at the structures, right? That's what it's all about in organic chemistry here. Okay? Cool. So, now we got this new way of looking at things. And we're going to look closely at this reaction here. And we're going to play a very fun game called the Spot the Difference game. All right, and specifically we want to look on both sides of this chemical equation. And what we want to look for is what bonds do we see are being broken in this reaction here, right? So what bonds are broken? As well as what new bonds are formed. Okay? But not only that, we want to also pay attention to these lone pairs here. So, what lone pairs sort of disappear from our reactant side? I'm going to run out of room. And likewise, we want to look for what lone pairs we now see on our product side that weren't there originally. Okay, so everybody take a second and see if you can't play the spot the difference game here. There's going to be one from each category here. So go through and see if you can tell which bond is being broken in this reaction, what new bond is being formed, what lone pairs do we see on the reactant side that aren't there on the product side, and vice versa. What lone pairs do we see on the product side that weren't there on the reactant side? Okay, so everybody just take a second looking at these structures here and play our spot the difference game. Okay, everybody see what bonds are being broken in this reaction? The bond between hydrogen and chlorine, right? So this bond appears on my reactant side and it is nowhere to be found on my product side. So this reaction is going to break that hydrogen-chlorine bond. What about what new bonds are being formed? Hydrogen and oxygen, right? So now I already had one hydrogen-oxygen bond, but now I have this second hydrogen-oxygen bond, okay? And now we're not only going to pay attention to the bonds, but also the lone pairs. So what lone pairs do we see on the reactant side that are no longer there on the product side? We got that extra one on our hydroxide ion, right? That hydroxide oxygen has 3 lone pairs. If I jump to the product side, water only has 2 lone pairs. So that lone pair goes somewhere, right? And then lastly, I guess to keep things color-coded here, and then lastly, what new lone pairs do we see appear on the product side that weren't there on the reactant side? The one on the chloride ion, right? It has 4 on the left or on the right and only 3 on the left. Cool. Okay, so organic chemistry is all about studying chemical reactions. Right? And like we said, we're kind of laying the groundwork now. We're kind of building up our tool chest to be able to talk about chemical reactions. Okay? But chemical reactions, as we can see from the above, is just the making and breaking of bonds, right? That's all a chemical reaction is. You make bonds, you break bonds. Okay? So make and break bonds. And bonds are, of course, made up of what subatomic particle? Protons, neutrons, electrons. What makes up a bond? Electrons. All right, so bonds are made up of electrons. So when we talk about studying chemical reactions, really what we're talking about is studying the movement of those electrons. Right? That's what's happening in a chemical reaction, is you're shuffling around electrons. You're changing who's bonded to who. Okay? So when I say we're going to learn to read today, what we're going to learn how to read are these electron pushing arrows, and they show us the movement of electrons in a chemical reaction. How the electrons are being shuffled around from the reactant side to the product side. Okay? So, again, we're going to call these electron pushing arrows. Well, that's what they're called. I didn't make it up. But okay. So I'm going to show you what these electron pushing arrows look like on that reaction that we were just talking about, and then we'll kind of pick it apart and we'll lay down some rules for drawing these arrows. Okay? So it turns out, so we sort of highlighted all these categories here, right? We said that this lone pair on my hydroxide ion seems to disappear from the reactant side. And then I have this new bond between oxygen and hydrogen on the product side, right? Well, it turns out that those are the same electrons. These 2 electrons that were in that lone pair in my hydroxide ion, they now become my new hydrogen-oxygen bond, right? That bond had to come from somewhere. It's made of electrons. Those electrons were originally sitting on that hydroxide ion, okay? Likewise, we said that this bond between hydrogen and chlorine broke, and then all of a sudden we got a new lone pair of electrons on chlorine. Well, where did that pair of electrons come from? the pair of electrons that were in that hydrogen-chlorine bond are now that lone pair that is sitting on that chloride ion. Okay? Just like when you balance chemical equations, you made sure that there were the same number of hydrogens and oxygens and chlorines. What you didn't really realize you were also doing is making sure that electrons were being conserved, right? Electrons don't appear out of nowhere. They can't disappear. So they're all accounted for in our structures here, all right? So how we would draw this new bond being formed is an arrow that starts at that lone pair and then points to that hydrogen atom where that new bond is being formed, okay? So this is an electron pushing arrow that shows a bond formation, a bond being formed. All right, and likewise, we got to show that hydrogen-chlorine bond being broken. So how do we do that? We have another arrow that starts at the bond and then points to that chlorine atom, because that chlorine atom is the one accepting that pair of electrons. Okay? So this one represents a bond breaking. And if you can't see that just yet, don't worry. We're going to sort of be practice. This is a practice makes perfect kind of thing. Just like when I showed you that little squiggly line and was like, that's propane, that's this molecule. And you were like, what the heck is this guy talking about, right? We just got to sort of practice it and go through it and pick it apart and all that stuff. But you're just going to trust me for now. These are these electron pushing arrows. The one shows a new bond being formed. The other one shows a bond being broken. Okay? So drawing these electron pushing arrows, we got some rules here. The first one is the tail of that arrow must start at a pair of electrons. Okay? So if we look back on this molecule here, all these examples are electron pushing arrows. The arrow starts at a pair of electrons, right? The tail of that arrow. So the head of the arrow must point at an atom. And that's the atom that's accepting those electrons. Okay, so we got these electron pushing arrows. The tail of the arrow, and let's just go back and look at them. The tail of that arrow is at a pair of electrons. It could be a lone pair of electrons or a bonding pair of electrons, but the tail of the arrow has to start at a pair of electrons. And the head of the arrow is pointing to an atom, right? And that's the atom that's going to accept that pair of electrons. Okay? So these are really important rules to keep in mind, because if you draw your arrows backwards, it is not correct. All right? So, and what we saw again was we saw one arrow represented a bond being formed, and the other arrow represented a bond being broken. And we're going to see this pattern over and over and over again, because that's what chemical reactions do. They make and break bonds, right? So let's leave some space, because we're going to add to our rules for electron pushing arrows, but let's just kind of make note about the sort of patterns that we're going to see over and over again. Bond formation. Okay, this is an arrow that starts at a lone pair and points to an atom in a different molecule. Oops. Right, so again, if we look at our bond formation here, it starts at a lone pair in one molecule and then points to a different molecule, right? It like bridges two different molecules in space there, okay? So that's going to be a bond formation arrow. A bond breaking arrow is going to start at a bonding pair of electrons. All right, and it's also going to end in an atom. It always has to end in an atom. But this is going to be an atom that shares that bond. Right, so these will end at an atom connected to that bonding pair. Okay? So, the whole shtick, for those of you who missed it, we got these arrows. They represent the movement of electrons. Chemical reactions are all about making and breaking bonds. So these arrows represent bonds being formed and bonds being broken. That's how we do this, okay? And this is kind of like the holy grail of information that you could know about a chemical reaction. It's kind of easy to know, oh, I mix this together and this comes out the other side. Exactly how the electrons are moving around, that's like the great piece of information that makes a chemist like know the crap out of a reaction or whatever. That's the holy grail piece of information that we would love to know about every reaction that we study. Some reactions, we know exactly how it works. Other ones are still kind of a mystery to us, all right? But that's sort of how we would represent this. So let's practice the crap out of this, all right? So I'm gonna draw some like a reactant side and a product side, and we're gonna try to draw in the electron pushing arrows here, all right? Okay, so again, play that spot the difference game. Are there bonds being broken? Are there bonds being formed? And then go back to those patterns that we talked about. See if you can't draw in our electron pushing arrow for this step in our reaction here. It's always going to be on the reactant side. Yep. These arrows lead to the product that you see. Okay. I'll give you a hint for this one. You only need to draw in one arrow here, and that would be a bond breaking arrow. All right, so again, if we just play that spot the difference game, we see that this bond is being broken. It's on my reactant side, but not on my product side, so I gotta break that bond. And I got this new lone pair that appears on my product side that wasn't there on my reactant side, right? So those are the same pair of electrons. So my electron pushing arrow is going to show a bond breaking. It's going to start at that bond between carbon and iodine and end just on that iodine atom. It is accepting that pair of electrons. Okay? Now, importantly, look up here for a second. It would not matter at all if you instead drew that arrow down here. I mean, it would look a little weird, but you could even, woo, boom. As long as it starts and ends at the right place, right? It's got to start at that bond and end at that iodide ion. What would be incorrect is having it go in the opposite direction, right? Your tail's in the wrong place, your head's in the wrong place. So this would be my bond breaking arrow. All right. So now let's do another one. again, you will only need one arrow for this particular step here, and it will be a bond formation arrow now. All right, so spot the difference. My chlorine on the left has 4 lone pairs, and on the right it only has 3, right? So this one's going to go somewhere, and I have this new bond that's being formed in my reaction. So those are indeed the same pair. So I'm going to draw an arrow from that lone pair to that carbon where that new bond is being formed. All right, and this one, starting at a lone pair and connecting 2 things in space, is a bond formation arrow. All right, so now let's do one that's slightly more difficult here. All right, and to complete this, what we call a mechanism, when we see those arrows, you're going to actually need to draw 2 different arrows here. One's going to represent a new bond being formed, and one's going to represent an existing bond being broken. All right, and I'm just going to sort of, we have these implicit carbons. I'm just going to sort of darken where they would be so we can remember they exist. Might help you see how these new bonds are being formed and broken. Okay, so again, if we just play that spot the difference game, what lone pairs do we see on the product side that aren't on the reactant side, and vice versa? My bromine has an extra lone pair, and my oxygen is missing a lone pair on the product side that it used to have on the reactant side. Okay, and if we look at bonds, we have this new bond between oxygen and carbon on the product side, and we have broken this bond between carbon and bromine on my reactant side. All right, so again, step 1 is to play that spot the difference game. What are the difference between lone pairs, and what are the difference between bonds on both sides? What bonds are being broken and formed? What lone pairs seem to like disappear, and what appear on our products? What disappears from the reactant side and appears on the product side? So I need to draw this new bond between oxygen and carbon. So these lone pairs, I'm just going to color them the same as, they're going to be pink because those are the lone pairs that are in my new carbon-oxygen bond, right? So drawing my bond formation arrow, it's going to start at a lone pair and end at that carbon atom, okay? And it's got to be the carbon atom. You can't point to the bromine, right? Because you're not forming a new bond between oxygen and bromine. It's a new bond between oxygen and carbon. So carbon is the one accepting that pair of electrons. All right, likewise, I'm going to color these electrons the same because this bonding pair of electrons between carbon and bromine, is now that lone pair on my bromide ion. And so I got to draw a bond breaking arrow where this pair of electrons jumps to that bromine atom. Again, these are electron pushing arrows, so you can kind of think about it. I'm grabbing these electrons at the tail of my arrow and I'm dragging them to where the head of the arrow is. I'm grabbing that lone pair on the oxygen and dragging it over to that carbon atom to form a new bond. I'm grabbing that bonding pair of electrons between carbon and bromine and dragging it so now it's only associated with that bromide ion. Okay? Again, we got two arrows here. This is a bond breaking, and this one is bond formation. All right, so one more where I want y'all to put in the arrows here. All right, and again, you will need two arrows to complete this one. So I got this new bond over here on my product side between oxygen and carbon, and that is this lone pair right here, right? That lone pair that disappeared from my reactant side. So I'm going to draw that bond formation arrow, okay? And are there any bonds being broken here? What bonds are being broken? The double bond, right? It's going to turn into a single bond. So I got to break one of those bonds, and that's just a normal bond breaking arrow starting at that pair of electrons, that bonding pair, and ending on that oxygen. That's why oxygen has one extra lone pair on my product side. It came from that bond there. Okay? Cool. All right, so now let's try drawing in these, or rather trying to follow these arrows, right? So I'm going to show you a structure with some electron pushing arrows, and you're going to draw me the product here, okay? One thing that I want to point out that we haven't really talked about up until this point, and so we can sort of add this to our notes here, and this is going to be a great kind of double check for as you're going through and drawing your structures, okay? So, first of all, we never exceed the octet of an atom. Okay? We also want to never break an atom's octet. All right, but there's one very important exception to that rule, that never break the octet rule. We were talking about formal charges. Does anybody remember that one time that we see that octet rule broken? Carbon when it has a positive charge, what we call a carbocation. So we can just note, except for carbocations. All right, those are the only times we're going to break that octet rule. So oxygen, nitrogen, never will have their octet rule broken. Okay? The other thing that I want to note here is if we look on both sides of this reaction, we see that what's the net charge on the left-hand side here? If I total up the charge of all my molecules here, this one is neutral, this one has a negative charge, so I have this net charge of -1. And if I look on the product side, I have that same net charge. This is what's called conservation of charges. Okay, charges can be one of the trickiest things when you're drawing structures. And so remembering this idea of conservation of charges, whatever the total amount of charge you have on the left is, you gotta have that same total amount of charge on the right. Okay, so let's just add that to our little list here of things to keep in mind. Charge conservation. All right, and another good example is that very first one that we did. This molecule on the left-hand side was neutral, so I have a net charge of 0. On the right-hand side, I made this negatively charged iodide ion, but I also made this positively charged carbocation, right? So I still have a net charge of 0. So just keep that in mind. It doesn't mean that you're not going to see charges. It just means that the net charge on both sides of that chemical equation have to be the same. Okay? And the last little thing that we're going to add to keep in mind, and this is something you're going to hear me say a lot, is count your carbons. Very easy mistake to make is to add an extra little stick or forget to add a little line or whatever, just miscounting your carbons. So always double check by counting your carbons at the end. All right, so now I'm going to put in some electron pushing arrows, and you're going to tell me what the product of these are. All right, so here's my electron pushing arrow, and y'all draw me the result here. What's the product of this step? So first of all, according to these patterns that we said that we were going to see over and over again, which one do I see here? Is this a bond formation arrow or a bond breaking arrow? Bond formation arrow. So first, and those are kind of almost the easiest to see because they're connecting two things in space that didn't used to be connected, right? That means that you're making a new bond between those things. So absolutely, this is a bond formation arrow, and I will forgive you if right now you drew it like this, right? But remember that really we want to sort of keep these things spaced out, and so we would want to draw it as that cross. Okay? That looks like crap. Let me redo this. right? But I have this extra bond here. And what's the formal charge on that nitrogen now? 0, right? It's got that lone pair. It had that extra lone pair, but now it's a bond. So now it's got its 3 bonds and 1 lone pair. And again, just conservation of charges. I had a net charge of 0 on the left-hand side. I gotta have a net charge of 0 on the right-hand side as well. Okay? And again, just counting carbons, right? You see me tap, tap, tap my screen a bunch. 1, 2, 3, 4. 1, 2, 3, 4. Just a very easy double check to do when you get done to make sure that you didn't actually add or forget a carbon. I'm sure at least somebody in here, when they were drawing their structures, at some point in time in their homework, accidentally forgot a line or drew an extra line. It's just the easiest mistake to make. All right, so let's do another one. Okay, so now I'm going to draw an electron pushing arrow, and you're going to draw me the product of this step here. Remember to go back to those patterns. Is this a bond formation arrow or a bond breaking arrow? So now I'm going to break that bond. I'm going to chop that bond. I'm going to be left with just my hexagon. And what's my other product? This one we know the name of. We haven't talked about many molecules yet, but I trust that you all know the name of that one. Water. Cool. And am I done?
Yeah, I was just going to ask how to do that part for the energy conservation.
Okay, so absolutely, the charge conservation, right? So I'm not done. Spoiler alert, right? Because I have not conserved my charges. I have a net charge of +1 on the right and a net charge of 0 on the left. Something's missing somewhere, right? So this is sort of tricky, especially when we're starting out here, is remembering these implied hydrogens. So let's just go in and draw these implied hydrogens on our reactant side here. How many hydrogens does this carbon right here need? 2, right? So in fact, all the ones around the ring need 2. And then I get to this one here. How many hydrogens should I put on there? Just 1, okay? Now, importantly, I broke that carbon-oxygen bond, so let me just draw them in over here. I didn't touch the number of hydrogens, right? So this still has that 1 hydrogen on there. Okay, so then how many bonds total does this carbon have? 3, which means that it has that formal charge of +1, right? 3 bonds, no lone pairs. And you can sort of also convince yourself that it got this pair of electrons that was in that bond snatched away from it, right? It had its perfectly complete octet, it was all happy, and all of a sudden somebody came along and took those electrons away, right? That oxygen did. So this carbon right here has that formal charge of +1 that leads to my conservation of charges. And if you are having trouble with your conservation of charges, carbon is often the culprit, right? Because of those implied hydrogens, it's a little harder to see, okay? So if you're ever running into a pickle with your charges, look at your carbon. That'll help. All right. So let's do a slightly more difficult one. Now I'm going to put in 2 arrows here. All right, so again, here is this set of reactants, and you're going to draw me the products of these 2 electron pushing arrows here, right? What do I get on the other side? So let's just look here. This arrow right here represents what? A bond being formed or a bond being broken? So this will be a broken. And what about the top one? So that's a formation arrow. Okay, so I've got my iodide now all by itself with that extra lone pair. That lone pair came from that bond. Okay, and now I have to draw this new sulfur carbon bond, and again, if you drew it like this, I would forgive you for now, but that's not how we do it, right? We want to draw it so they're all evenly spaced, so you would just draw it pointing the opposite direction. I get that, like, keeping things consistent with how they're laid out on the page is sort of helpful to see what's going on. The problem is that if you walked into a room full of chemists with your structures drawn like that, everybody would snicker at you, right? It's like just not the way that it's done, right? So we want to space those things out. What's up?
So if you drew like a cross like we did before, that would be wrong too?
Well, there's only 3 bonds on that carbon, right? There's not a total of 4.
Oh, okay.
Right? So the cross is specifically for when there's 4 bonds, and you gotta space them all out 90 degrees. Okay? But I do have something, and actually let me just color code real quick, that this lone pair now became this bond, and then what's wrong here? Am I done? Conservation of charges, right? So I'm missing that formal charge, and where is that formal charge supposed to go? On the iodide, right? 4 lone pairs on that halogen means that it gets that minus sign. All right, so one more here. Right, and now we have in the same molecule 2 sets of arrows. All right, might look weird, but just apply that same logic, try to classify them as bond formation or bond breaking, and go from there. All right, so this one right here, this bottom one, is that a bond being formed or a bond being broken? So we got one being broken, and what about this one? All right, so that's starting at a lone pair, and it's reaching to this atom. That atom is connected, so it's not like separate in space, so this is an example of one that's a little bit harder to see, but starting at that lone pair and reaching down to that carbon atom, this is indeed a bond being formed here. Okay, so let's break this one first. We've seen this kind of over and over again, so I think it might be a little bit easier to see. I'm going to pop off that chlorine. Okay, it's going to have 4 lone pairs, which means it should have a formal charge of -1. Okay, and so we said that this is a bond formation, that other arrow, but there's already a bond there, so what am I supposed to do? Double bond, absolutely. So how we would draw our other product here is now with this carbon-oxygen double bond. All right, so now, does this reaction actually occur? Who the hell knows? That's not what we're talking about yet, right? We will get to the point where we study these reactions. Truthfully, I specifically picked reactions that do occur and that we will study throughout the semester, but that's not what we're doing right now. We're not actually talking about reactions. We're worrying about drawing these arrows in. Can you put these arrows in if I give you a reactant and a product, and can you follow those arrows? That's what we're focusing on, right? We will use these arrows to talk about chemical reactions. We're just learning how to read at this point, okay? All right, so there is one more set of arrow that we're going to see that follows a slightly different pattern than what we talked about. Bond formation and bond breaking. This is now, it's kind of a more rare thing, although it occurs in some of the first sets of reactions that we're going to study here. This is an electron pushing arrow that represents both a bond breaking and a new bond being formed all in one shot. Okay. What's going to make these sort of easy to see, or our pattern that we're going to look for, is they will always start specifically at a pi bonding pair of electrons. Right? And then they will point to an atom in a different molecule. All right. So let me show you an example here. Okay, and I'm going to draw the full Lewis structure of this molecule out so we can sort of see and keep track of these these hydrogens here. But this would be a carbon-carbon double bond. We'll just do a very small molecule here, 2 carbons. Okay, these carbon-carbon double bonds are going to be one of the first sets of functional groups that we study, so we want to sort of make note of these particular arrows here because, again, they fall out of our normal pattern. All right, so let's just put a proton here. So this would be an example of one of those electron-pushing arrows that represent both breaking and formation. Okay, all in one shot, all in one arrow. All right. So I'm gonna show. Let me just kind of visually illustrate what this arrow is representing here. Actually, let me make a copy. All right. So again, remember these electron pushing arrows. It's like you're grabbing this pair of electrons and dragging it over to that new hydrogen, right? So how I could sort of illustrate that is I have this bond here, right? but it's going to be broken, and now I'm going to drag this over and create a new bond between the carbon and the hydrogen, right? So I broke this existing carbon-carbon double bond, and now I've formed a new bond between carbon and hydrogen. Okay, so it's both of these all in one shot. I didn't do my charges, if that was your question.
I'm just asking if it matters which carbon you come off.
In this case, no, and it will when we start studying these reactions and all that jazz, but at this point, just pick one. Yep. All right, so the product of these arrows here, again, I'm picking that pair and dragging it up. Would be now I have these 3 hydrogens on 1 carbon, but still only the 2 on the other. And we do got to worry about charge conservation. So where's that positive charge that's being conserved? On the carbon, right? There's one of those carbons that got that pair of electrons snatched away from it, right? And so that carbon is going to be left with a positive charge. And again, I drew out the full Lewis structure, so it was a little bit more obvious, but that's what's going to make these a little bit harder to spy is the charges, because in our bond line structure, we don't explicitly draw in all those hydrogens all the time, right? So we just got to remember to sort of go and double check when we're worried about charges. All right, so let's look at another example here, see if y'all can't figure out the product of this step. So kind of visually here, right? I'm going to take this, what was double bond, and now it's going to reach out and form a new bond with that bromine. So I'm going to have that bromine. Okay. What else am I missing? The other bromine, right? I mean, we got to have the same number of atoms on both sides. So yeah, and there was this bond that broke, right? So it's actually a bromide ion, right? Bromine floating around all by itself with a negative charge. And then what else am I missing? Conservation of charges, right? So again, that positive charge on that carbon that got that pair of electrons taken away from it. And again, you can sort of count hydrogens and convince yourself there was 1 hydrogen on this carbon, so there's only 1 over here. 3 bonds, right, at positive 1 formal charge. Okay, cool. So now I'm going to tell you that it actually turns out that in this reaction here, there's a second step. And the product looks like this, and you're going to put in the proper electron pushing arrows. Whoops. So remember, we want to play just spot the difference first. What new bonds are being formed? What bonds are broken? What lone pairs are missing or appear? Do I have any bonds being broken in this step? No. Do I have any new bonds being formed? All right, so I got this carbon-bromine bond I got to form with my arrows here. And where did that pair of electrons come from? On that bromide ion. Absolutely. So I'm just going to pick that pair of electrons up, and I'm going to drag it over to that carbocation using the ugliest arrow you've ever seen in order to create my new bond. Okay? Cool. And anyway, bottom line is we learned about these electron pushing arrows and why are they going to be super important, because again, in organic chemistry, what we care about is chemical reactions, and chemical reactions are about making and breaking bonds. Bonds are made of electrons, right? So when we talk about chemical reactions, really what we're talking about is the movement of electrons, and that's what we can illustrate using those electron pushing arrows.